Hello, everyone. Deep inside almost every single piece of modern tech we use, yep, our phones, our computers, there's this secret hero working away quietly. It's a tiny circuit, but it's also a super important bridge. It turns the messy, kind of chaotic language of the real world into the clean, precise language our digital devices understand. Today, we're going to unlock its secrets. Welcome to Cognito Key. Here, we love making complicated stuff simple and clear. So let's jump right in.
Seriously, have you ever just stopped and wondered about that? How does the smooth, continuous sound of a guitar or all the beautiful colors of a sunset get captured so perfectly inside a digital file? Well, the answer lies in solving a really fundamental problem with nature itself.
You see, everything in the natural world, sound, light, you name it, is analog. These signals are like continuous flowing waves of information. And while that's really beautiful, for technology, it's a bit of a headache. It's a world filled with noise.
Okay, so here's the main difference. Imagine an analog signal is like a flowing river. It's smooth, it's continuous, but if you throw even a small rock in there, the ripples mess up the whole stream. That's noise. Now, a digital signal, think of it like a set of stairs, right? Each step is a clear, discrete value. Even if one step gets a little chip, you still know exactly where the next step is. It's just so much more robust, which makes it the perfect language for our computers.
So, how do we get from that noisy river to those clean, perfect stairs? We need a translator, right? We need a bridge. And that brings us to the hero of our story today, the sample and hold circuit. It's a really elegant solution to a very big problem.
At its core, the sample and hold circuit does exactly what its name suggests. Just imagine trying to draw a picture of a car that's speeding past you. It's almost impossible, right? But what if you took a quick snapshot with a camera? The car is frozen in that picture, and now you can draw it easily. This little circuit does the exact same thing for an electrical signal. It takes a snapshot of its voltage at one precise instant.
It's really just a simple two-step dance. First, it samples. It captures the voltage. And this happens incredibly fast, sometimes in just a tiny fraction of a second. Then it holds. It freezes that exact value, holding it perfectly steady so that the next part of the system has time to read it. Simple, right? Sample, then hold. Now, that sounds simple enough, but how does this little circuit actually pull off this magic trick? Come on, let's take a look under the hood.
So there are three key players in this whole operation. We've got a switch, which acts like a gate. We have a memory element, that's our capacitor, and we have a stabilizer, which is an op-amp that makes sure our signal stays nice and steady. Let's see how this team works together. Okay, so during the sampling time, the switch is turned on. You can think of this just like opening a camera shutter. The gate is open. This lets the signal's voltage rush in and fill up the capacitor, which is kind of like the camera sensor. It charges up almost instantly to capture that one precise moment. And then, just as quickly, the switch is turned off. The gate slams shut. Now that electrical charge is trapped inside the capacitor. It has nowhere to go. And this allows the capacitor to hold that voltage, perfectly frozen in time. The snapshot is taken. And if you do this sample, hold, over and over and over again really, really fast, you transform that messy, continuous analog wave into a clean, predictable stair-step signal. Each of those steps represents one frozen snapshot, one moment in time that a computer can easily understand and convert into a digital value. Pretty cool, huh?
But of course, not all sample and hold circuits are created equal. To be a real hero, our little circuit needs to be super fast and super precise. So what exactly separates a good circuit from a truly great one?
It all comes down to speed and accuracy. First, it needs a very short acquisition time. That's how long it takes for the capacitor to charge up. The faster, the better. Second, you want low voltage droop. This basically means the capacitor can't leak its charge while it's holding it. Otherwise, our snapshot would start to fade. And finally, aperture time. The tiny delay between the hold command and the switch actually closing has to be almost zero to make sure we capture the exact moment we want.
So now that we know how this amazing little circuit works and what makes it so great, where do we actually find it in the real world? Well, the answer is pretty much everywhere.
This circuit is absolutely fundamental to almost any modern electronic device. In data conversion systems, the heart of digital music, it's sampling the sound wave over 44,000 times a second.
It's inside digital voltmeters, freezing a voltage so you can actually read the number on the screen. From engineering tools to the data systems that run our world, this little circuit is working nonstop, right behind the scenes.
And really, that's the key takeaway. This simple two-step process is the bridge between our fluid analog reality and the precise digital universe we've built. It takes all that chaos and gives it order, one perfect snapshot at a time. So the next time you hear a crystal-clear digital song, you'll know the secret hero that made it all possible.
If you enjoyed this explainer and you want to unlock more keys to understanding the world around us, please subscribe to Cognito Key. And don't forget to like this and share it with someone you think might find it interesting. Thanks for watching.